the rotation of the body requires different approaches than particle motion analysis, because the size or the shape of the body must be considered. If you look at this example here, the one disk is rotating about A, so this is a rotational axis. This is rotational motions, so it has something to do with the angle change. So in the rotational motion, the velocity refers to angular velocity, and then usually we used omega. Omega refers to angular. Then since this is still the velocity, it has a direction as well. Right now this is disk, so if you think this is just on top of the plane, the omega, which is angular velocity, has a direction that coming out of this plane. So likewise, in this rotation, we have a certain reference line, okay? Because in order to measure the angle, you think about one line of reference, so from which you just measure the angle, and per time the angle change, right? So that's why d theta over dt become your instantaneous angular velocity. And many times we use omega, or that is the time derivatives of theta. That's why we sometimes use theta dot. So theta dot or omega refers to angular velocity. And on this slide, this one shows three kinematic equations of motion. Right now, if we know the angular acceleration, which is alpha, so in a rotational motion, alpha refers to angular. Given initial rotation, initial angle plus angular velocity times t becomes your current angular velocity. And if you want to find the angle change, the angle is equal to initial angle and plus the initial angular velocity times t and 1 over 2 angular velocity and time square. When we talk about the rectilinear motion, your velocity can be determined by initial velocity and constant acceleration time t, and your position s can be determined by your initial position and initial velocity time and 1 over 2 ac t square. So as you see that these are almost same, but in the rectilinear motions we talk about the velocity and position of change over the straight line motion, but in rotational motion we talked about the angle and angular position change. But kinematic equations exactly have the same form. For me to help you to understand the concept more, let's do one example here. Right now, two pulley system is connected, and then the motor rotates with the constant angular velocity of 2 radian per second square. So this is acceleration. So alpha in here, alpha is 2 radian per second square, and I want to determine how much the weight has been lifted after the motor has turned 1 revolution. Okay, so which means the smaller motor turned 1 revolution, and how much the weight W has been lifted. Okay, then let's look at this one. So right now the motor and the pulley is connected through this kind of strap. Okay, then if you're thinking about any points on the strap, so let's say this is P1, then this P1 is just rotate, right? So any point of this P1 velocity is like that, and that could be the same velocity of here, right? So the velocity of this point and velocity of this P1 point should be the same. That means the velocity of this point should be the same, right? So let's say this is a B point, and let's say here is A point. Then the VA is equal to the VB, and this is BP1 anyway. Okay. And then what is a VA? So velocity of A, this is rotating about this is axis, rotating about the axis of the motor. And then when circle is rotating, okay, when circle is rotating, the velocity of on edge is determined by the r times omega, which is angular velocity of that rotating disk. So which means that the VA, okay, VA is determined by omega a. The omega is angular velocity of this motor, and RA, right? RA is equal to, in here, we do not know what's the omega. So omega B, the larger wheel, and then your RB, that should be the same, right? So your omega B is equal to omega A RA over RB. So right now the RA RB is given. RA is 0.15, RB is 0.5. Okay. Then omega A. Okay. Now this one, the omega, the small motor has turned 1 revolution, right? 1 revolution, and it has the certain angular acceleration. So omega is equal to omega naught plus angular velocity, angular acceleration time t. Then we know that it starts from 0, so the angular velocity of initial angular velocity will be 0. And then we know our alpha is 2 and t. So right now omega A is the function of time, which is 2t. So then we replace, this is 0.3, omega A is 2t, okay? So this one becomes 0.6t. So we figured out what would be angular velocity of the larger wheel as a function of time. Okay, then I want to find the velocity of this point. Okay, so let's say this is C. Right now, this whole wheel has a certain angular velocity, which is omega B, but this one is the C point has a different radius than the larger wheel B. So I want to velocity of C point. Okay, that is equal to radius R, which is 0.3. and omega B. Okay, so this one should be 1.8t. Okay, so now that the velocity of C is the same as velocity that pulling the weight. Okay, the same as velocity. So we have this information. So let's calculate how much it took time for this motor to turn 1 revolution. Okay. So we know that these kinematic equations for rotational motions. So one revolution is 2 pi, okay, which is about 6.28 radian, which is we have the 0 angular position, and then 0 initial angular velocity, and 1/2 IC AC is 2, right? This is 2 and time t. So from here, we can compute how much it took for a small motor to turn 1 revolution. The time is 2.51 seconds. So from here, your acceleration of AC, which is dvc over dt, is 1.8. So it has just meter per second square. So this one just has the constant acceleration. So if you want to know how much this one has been lifted, you go back to the linear kinematics equations of motion. So this is SV naught t and 1 over 2 ACT. So this one, we just consider that the initial one is our reference, that's 0. And then everything starts from 0. So the initial velocity must be the 0, right? And 1 over 2 and 1.8. And our time is 2.51 square. So that should be 0.565 meter. So right now, in this example, we used the kinematic equations for rotation, like this one or this one, and also in order to compute this kind of linear motion as well, that's why we had to use this equation as well. And then one more thing that you have to remember is that when the pulley system, because the pulley system connect the two wheel, so this equations is valid because the velocity on here and h velocity is here. So in order to satisfy these conditions, then the h velocity, that's why that h velocity is determined by omega r. So omega a RA and omega b and RB must be the same. Now let's look at more general rigid body rotation. In this 3D kind of drawing, in this disc is a flat disc is rotating about this O. Okay, and then this is rotating at angular velocity omega. Okay, this is our angular velocity omega, and I told you that angular velocity omega is vector. It has the direction perpendicular to the plane that is rotating. Okay, and then if you have angular acceleration also has the same direction of angular velocity. Okay, so that angular acceleration is the time derivatives of omega. Okay, that's why it has a dot here, and this omega dot is the same as the this theta dot is same as omega. And then in this kind of conditions, let's say if you want to get the velocity of any arbitrary point P or acceleration of point P, then how we can determine the velocity and acceleration of any arbitrary P on the surface of your rigid body. Look at this circle. So right now, let's just imagine that we look at the disk from the top, okay, and this is center, and this is kind of let's say this is a reference line, and your theta can be measured from this horizontal line, and then let's say this is arbitrarily my point P. Then if this disk rotating about the center, the velocity should be tangent to the path, so velocity direction looks like that. Okay, and then we use the polar coordinate system. So in here, instead of using polar coordinate system, let's use tangential and normal component system. Okay, so that means this is your tangent direction, so I say this is UT, and then the normal component is perpendicular to your tangent, So let's say this is normal component direction at this given time. So let's say I want to put the position first. I want to determine the position. So position of P, okay, is, we can just use the vector. So which means from here to here. So if I just draw a line, this is my vector position P. Okay? And then I can write down this vector like magnitude and direction. So my magnitude of the radius is just r, and then direction. Right now the position vector direction is coming from center to the outer. So I can write down this is my normal vector like that. And how about the velocity? So let's try to see the velocity of the P. So my velocity of Vp is equal to your position vector time differentiation, right? Like that. Then what is this one? So in order to I already explained when I talked about the polar coordinate system, but if I just to show you again, if you a little bit zoom in this area, so let's say this is your curvature, and then this is your P points, and then certain time later this one move to P prime, for example, and then the change of angle is delta theta. Think about the length of arc here, okay, and then the length of arc, okay, length of arc is delta, let's say S. That's the length of arc, and the length of arc should be r times delta theta, right? Then the velocity is drp over dt, so that's the same as limit delta r over delta t when delta t goes to almost to 0. The delta r is the change of your position, right? So that means this is your rp, and the next time this is rp prime, rp prime minus rp. So this delta rp is rp prime minus rp. That is the vector here, right? This vector. So this is delta r. But since this is small, delta r is almost close to delta theta, okay, delta theta, which is r delta theta. So I just replace this delta r is r delta theta over dt. However, I think about I need to think about direction. The direction at this time, the velocity of direction is the tangential direction, right? So I just use tangential direction unit vector like that. Then it becomes like r theta dot and ut, okay, ut. So I know that my velocity Vp at this time is determined by r theta dot, which is r omega, and the direction is tangential direction ut, okay, ut. So if I represent the velocity p, so the velocity p is r omega ut, like that. Or if we want to express this one in other form, we can write down like omega. Omega has the direction which is pointing out from this plane. So let's say that's the k direction, and cross product and your rp position vector. So why this equation is same as this one? right now, if you look at the vector, so I can write down this one is omega k cross product of r u n vector, because your rp was r u n. Okay. Then look at this one. So that means if you do the cross product between k and un, and that should be the same as ut. Is it true? So let's look at this cross product. So this is right hand rule. Okay. So as long as you use the right hand rule, your second index should be k direction, and third index is un direction. And let's see, when you do the cross product between k and un, then the result in ut direction, right? Because in here, in this example, k is coming out of your plane. Okay, so this is k. So k is coming towards you, and un is this way. Okay, so if you just make your angle according to the right hand rule, your thumb will direct it to ut. Okay, that's why this is correct. So so simply we can say, as long as you know the direction of omega, so uk times cross product rp, or sometimes maybe you can just say my vector angular velocity and the position vector cross product. Okay, so this is just vector notation, for the velocity. And how about the acceleration? Accelerations, you have to take a time derivative of your velocity, right? So if you just keep doing that, I just used the vector cross product rp dt. Okay, then I just do the cross product of dt and cross product rp plus cross product of drp dt. Then this one, this d omega over dt becomes what? It becomes acceleration, right? This is acceleration. So I can just put the alpha vector and cross product rp and plus omega, and then this is the same as this one. So this is omega cross product rp. So this is a vector form of your acceleration of p point. Well, let's just look at let's just a little bit unpack those kind of vector. So I know that your alpha, if alpha vector can be written using the unit vector, so alpha vector is ak, and cross product r is r u n, and plus u, as we said before here, this is omega k cross product omega k cross product r u n cross product. Okay, then just look at k u n k u n. Okay, so if you do the cross product between k and un, okay, k and un, then the result is ut. Okay, ut. And then if you do the k cross product ut, then what's the resultant vector? So if you do the k cross product ut, so if you think about this is your second index is k and third index is ut, then your thumb is directed to negative un. Okay, so the result is negative un vector. But these are all scalar, so that's why we put negative omega square r un like that. And then if you do the k cross product un, that's ut, so ut vector and alpha r equal. So right now your acceleration becomes this form as well. So this is purely vector form, and this is a little bit unpacked form. Okay. Then this is tangential component, and this is normal component. Okay. So because this is ut and this is un, so if you think about the acceleration of p, so we have alpha r tangential component of accelerations and omega square r normal component of normal direction. Then why we put the negative here? Because when you think about the acceleration at p, so there might be some acceleration along this tangential, that's tangential component, which is alpha r. And because this is rotating, there is inner component of tangential, inner component of accelerations, which can be determined by omega square r, but the direction is a negative because we define the normal component outward is a positive. That's why inward should be negative. That's why the negative means you have normal component that pointing to the center. Okay. So this is kind of summary. So right now, if you want to find everything is rotating about O with this certain angular acceleration, angular velocity, your vector v is your vector omega cross product vector ra. Okay. So this is nothing more than omega r and ut direction, because this is ut tangential direction. And how about the acceleration? Acceleration has a tangential and component. This is tangential, okay, and this is normal. So this is tangential, normal. So this is purely vector expressions. But we know that this is alpha r ut direction and minus omega square r normal direction, like that. Okay. So in terms of scalar, alpha r is always tangent component of accelerations, and omega square r is normal component of your velocity of any point A. Then lastly, let's look at the example. I have to put the positive alpha here because this is rotating clockwise, and decreasing acceleration could be positive because counterclockwise is a positive by default. So when everything is rotating to the clockwise but decreasing means the acceleration actually should be positive. But right now omega is 2, so that's why I put the negative here. And then I want to find acceleration point A. Okay, so acceleration point A, if I just write down purely vector form, and this is r and omega r, and then omega r, like that. So in here, if I just look at my A, so this could be this outer should be and then this is your tangential direction, like that. So what is my r? Okay, what is my r? So r is from here to here. That's my r. So your r vector. So right now your r vector is your 0.4 I and 0.3 j, right? Because this is my x and y at this given point. So along using this one, I can write down this 0.4 and 0.3 j. And then omega should be negative 2k. Okay. Oh, I'm sorry. This one should be alpha. And my alpha is 4k. Okay. Then we can just use this one. So let's just try to do that. So my acceleration is equal to alpha r ut, alpha r ut So my alpha are 4k, and so if I just follow this pure vector formations, 4k cross product r plus my omega is minus 2k, and cross product of and 2k, and my r, so r is 0.4 I 0.3 j. Then let's try to look at this one, k cross product I. So k cross product I becomes j, so and then k product j, negative I, right? So that's 1.2 negative I, like that. And how about this one, k product j? So let me just, and let's do this one first. K product j, negative I, but we have a negative one here, so that is positive 0.8 I, and k cross product j. Okay. So kj product, cross product j is negative I. Kj, this is I. Okay, so this one should be negative j. Okay, j, and this is positive 0.6 I. And then we have one more, kj, so we have to do one more here. Kj is negative I, right? So but we have negative, negative, positive, and one more negative is minus 1.6 I. And then ki is a j, but we have a negative here, like that. And then in the front we have 1.6 j, 1.2 I. So this is equal to minus 2.8 I, okay, and then 0.4 j. So that is our kind of answer, okay, as a vector form. So if I just drew that, this is negative 2.8, so this is our x right now. So the acceleration is like that. This is negative 2.8, and it has a positive j component, so it has this one. So this is negative 2.8, and this direction is 0.4. So acceleration is in this direction right now.